So this week we're going to be diving into Chapter 11. This is Heating the Atmosphere. This is really what's going to give us our basis for the next few chapters. This chapter really lays the groundwork for us talking about weather and climate. So, to begin with, what is the difference between weather and climate? Weather is a state or condition of the atmosphere at a given time and place. It is very short-term and constantly changing. Weather descriptions generally are valid for a smaller area than climate descriptions. Whereas weather is for a given time or place, climate is basically the summation of daily weather conditions, including average and extremes. Climate is much longer term and changes less frequently than weather. And the climate descriptions and statistics are generally valid for larger areas. Okay, so weather is both a very small area spatially and temporally, whereas climate covers much larger areas in terms of space and time. So climate is what you expect in winter, or weather. Weather is what you get. So climate data can't actually predict weather. For instance, if you live in the southern tier or in northern Pennsylvania like I do, you tend to expect a lot of snow for most winters, especially if you live over near Lake Erie. You get a lot of lake effect snow. Very cold winters. You have a shorter spring season. You have milder summers. Whereas in southern Pennsylvania there are a few weeks of the year where they hit 100 degrees. Southern New York, northern Pennsylvania, we're usually looking at highs in the 90s, so it's slightly cooler during the summer, but it's a much shorter summer season too, with the fall starts a little quicker. So climate is what we expect. We expect these changes to happen along certain times and the kind of range of temperatures, but weather is what we get. Weather is that daily highs and lows, and if it's going to rain or if it's going to be sunny. So weather and climate elements are properties of the atmosphere and are measured regularly. So what this means is temperature and humidity are both elements of weather and climate. Cloudiness, precipitation, air pressure, wind speed and direction. These are all different elements that make up both weather and climate. And these are dictated by, in part, by the condition of the atmosphere above a region. So when we talk about atmosphere, this is just briefly looking at a 1 year look at the weather in the Jamestown area. It's kind of hard to read, but it runs January to December. So here we're just looking at monthly low temperatures and monthly precipitation. And it's the blue are Jamestown and the magenta is New York State as a whole. So what is the coldest month in Jamestown? Well, if you look here, February is the coldest. And it's interesting to note that Jamestown overall tends to be slightly cooler, tends to have slightly lower lows than most of New York, with the exception of these winter months. It's actually slightly warmer in the winter months in the Jamestown region. And then here we have our monthly precipitation. And the wettest month in Jamestown, as you can see, is actually this is June. So June typically has the highest amount of rainfall in New York. Or in Jamestown, New York. Here we go. September as a whole for the entire state of New York. Okay, there we go. So what is the actual chemical composition of the atmosphere? When we talk about the atmosphere, we're like, oh, it's air. Well, that's cool. What is air? So dry air is made up primarily of nitrogen. When we talk about air, we think about oxygen. That's what we need to survive. But the majority of the air is nitrogen, 78%. Oxygen is just about 21% of the composition of the air around us. Another 0.04% is carbon dioxide, and then there are extremely small portions, we're talking parts per million, of other gases such as helium, methane, hydrogen. 99% of the atmosphere is oxygen and nitrogen. But these two gases have very little effect on the weather. These are two very stable gases, so they are not the ones driving the changes. So we talk about the atmosphere, we know the chemical composition. Well, we also need to talk about physical composition. So we're talking about variable components. These are components that change depending on the environment. So the first is water vapor. This makes up about 4% of air's actual volume. This water vapor is what forms clouds and precipitation. And the water vapor actually absorbs heat energy that is radiated from Earth. Okay, the second are aerosols. These are tiny solid and liquid particles. Water vapor can condense onto solids. So when we have a tiny solid particle that is suspended in the air as an aerosol, so it's too light to really settle down to Earth with any significant velocity, water vapor actually starts to accumulate and condense onto these solids. These aerosols then reflect sunlight back, and this is what helps color our sunrise and sunsets. Okay, so if you've ever heard the phrase, red in the morning, sailor's warning, red at night, sailor's delight, we're talking about the concentration of aerosols and water vapor that's giving these sunrises and sunsets their colors, which is why, a red sky in the morning usually indicated that there was some significant cloud with aerosols and water vapor in it moving in. When we talk about the atmosphere, you hear a lot of people talking about the ozone, and we're damaging the ozone layer and impacting the ozone, but what does that actually mean? When we talk about ozone, the ozone is really a name we give for a chemical composition of oxygen that has 3 atoms of oxygen, so O3. The distribution of this is not uniform throughout the atmosphere. It is concentrated about 10 to 50 kilometers above the Earth's surface. This ozone layer absorbs UV radiation from the sun that is harmful to life on Earth. Now, human activity is actually depleting the ozone by adding chlorofluorocarbons, or CFCs, into the atmosphere. Chlorofluorocarbons were commonly found in radiators, air conditioners, dehumidifiers, and refrigerators. They are also found in cleaning solvents and propellants and spray cans. Now, there has been a significant movement to really reduce the amount of chlorofluorocarbons used in some of these, such as air conditioners, but there's still a significant amount of use with these, and that's having an impact on the ozone as they're, if the chlorofluorocarbons contained within them, they're not disposed of properly, they're released to the atmosphere. And this is just showing the ozone in parts per million. So like we said, the ozone is really a concentration of that 3 atom oxygen structure. So you can see it really right about, that's like 30 kilometers above the Earth's surface is really where we start to peak in the concentration of ozone. So this is just a summary question: is air a specific gas? So like we just discussed, no, it's not. It's a combination of nitrogen, oxygen, a number of other gases put in there, but also the air doesn't stay the same in terms of composition vertically. As you see here, we have a higher concentration of that O3 as opposed to any sort of other structure, O2, N2, hydrogen. So now we need to talk about this vertical structure of the atmosphere. How does it change as we move further from our surface? So air pressure varies with altitude, becoming lower the higher one goes. Because the higher you go, the less air there is above you pressing down, right? So pressure is how much force is being pushed down onto something. Well, if we go up higher, we're above more of the atmosphere. We have less of it above us, so it's not pushing down as hard. So at sea level, air pressure is about 1,000 millibars, or 14.7 pounds per square inch, PSI. We typically use PSI when we're going to be talking about pressure units. Half of the atmosphere is actually below 3.5 miles from Earth's surface. So right here, 3.5 miles below or above Earth's surface, this is where 50% of our entire atmosphere exists. 90% of Earth's atmosphere exists below 10 miles. So right about here, this is where 90% of our atmosphere exists. Okay? And if you look at Mount Everest, you climb to the top of Mount Everest, we're about 8.5 kilometers in, okay, sorry, here's 10. Here's 10 miles. Mount Everest is about 8.5 kilometers tall, but we're looking at 75% probably of Earth's atmosphere exists below the peak of Mount Everest. So the air is extremely thin once we reach that height, meaning that there are fewer and fewer gas molecules per area volume. That's per basically there's fewer gas molecules there, so there's larger spaces between the molecules. There we go. They same number of molecules, much larger volume. There we go. Now the vertical structure can be broken up into 4 layers. The first is the thermosphere. This is the highest layer of the atmosphere and contains only a small amount of gas molecules. This extends from 50 to 90 miles above the Earth's surface. Temperatures actually increase with height in this layer. Third layer down is the mesosphere. This extends from about 30 to 50 miles, and temperatures decrease with height in this layer. Second is the stratosphere, and this is probably the one we think of most when we're talking about flight, airplanes, space exploration. This is the second layer and extends from 7 to 30 miles above the surface. Temperatures increase with height above 12 miles in this layer, as the ozone in this layer absorbs UV radiation from the sun. And then the troposphere is actually the lowest layer of the atmosphere, extending to the surface. Okay, so the troposphere is what surrounds us. This is the layer where weather actually occurs. Temperatures decrease with height. Sorry, my contacts are really bothering me today, so I apologize about the blinking on this video. So this is just showing temperature variations between the layers, and this is really how we came up with these layer boundaries, was these abrupt temperature changes. So here we've got our troposphere, and we start to reach a point where the temperature stops dropping and stabilizes for a bit and starts to actually increase again. And then the boundary between the stratosphere and the mesosphere, called the stratopause, is where we have the temperatures stabilize, they stop increasing, and then they start decreasing again. We go through the mesosphere, we reach the mesopause, where the temperatures stop dropping, stationary, and then start to gradually increase again. Okay, so those boundaries, the tropopause, stratopause, and mesopause, are what dictate the changes from one section of the atmosphere to another. I will post this video link for you on the class website this evening. So before we discuss why those temperature variations occurred, we need to start discussing the Earth-Sun relationship. To understand this, we need to start with the way the Earth moves. So the Earth has 2 different major motions. It rotates on its axis, and that's once every 24 hours. Now this axis is not vertical like we tend to think and see depicted. It's actually inclined at about 23.5 degrees, always in the same direction. It then revolves around the sun while rotating on this tilted axis. So the seasons on Earth are a result of the Earth's changing orientation to the sun and the changing length of daylight. So as this Earth is tilted, here's the sun, here's Earth. As it's tilted, it moves around the Earth, or around the sun like this. So the portion that was tilted towards the sun at one point in time is tilted away from the sun at another. This is where we get our changing daylight lengths and our changing seasons. The tropics of Cancer and Capricorn are the furthest north and south lines of latitude where the sun may be seen directly overhead and mark the beginning of summer and winter. So we have the equator, and this is the central line basically through the middle of Earth, correct? So the Tropic of Cancer is 23.5 degrees north latitude. Tropic of Capricorn is 23.5 degrees south. Okay, these are where you really start to get the beginning of these seasons, the change between summer and winter. So the Tropic of Cancer is where you get your summer solstice on June 21st. And the Tropic of Capricorn is where you get your winter solstice. Okay. So we have the sun approaching. Tropic of Capricorn has its solstice here, so that's when it's closest to the sun. It gives you your winter solstice. Tropic of Cancer is pointed away from the sun. Spring and fall equinox, the sun is directly overhead on the equator. And then summer solstice, when you have your beginning of summer, Tropic of Cancer is facing away to the sun, Tropic of Capricorn is facing, or sorry, Cancer is facing towards the sun, Capricorn is facing away. Jamestown, New York is at 42 degrees north of the equator. So the sun's apparent motion in the sky, if we're looking at summer equinox, the sun is never directly overhead. It's still mildly to the south of us as it rises and falls. As we reach a spring or fall equinox, you can see that it always stays in the southern region of our sky. In winter solstice, it is right on the southern horizon. Okay, so rising and setting in a more south direction as we get closer to winter, and rising and setting in a more north direction as we get close to summer. So if you've ever, if you live in New York, you drive 86. I did a lot of driving in it around November, December, and I would be leaving the eastern part of the state at about 5, 6 o'clock in the morning, and the sun would be rising to the east, but it would always be east and south, so it was always like right along my driver's side the whole time I was going. So that just made it really apparent how far south that sun actually is. It never reached overhead. It was always right in my eye right here. So the northern hemisphere is tilted toward the sun during the summer, causing solar radiation to reach the hemisphere at a higher angle and have a greater intensity. The northern hemisphere is tilted away from the sun during winter, causing the radiation to reach the hemisphere at a lower angle with less intensity. The relationship with the southern hemisphere is the exact opposite, resulting in opposite seasons. So here we're looking at the equatorial latitudes, and this is how the sun's radiation would hit it. And then the middle latitudes, the sun's radiation approaches it during the summer here. And then the polar latitudes, it never reaches this high intensity angle, right? Even at the height of summer, that polar area is never directly facing the sun, so it's always at this lower angle, so it's got less intensity and less radiation. So like we discussed before, 4 days of the year have special solar significance. Our summer solstice, which is June 21st, this is where the sun's vertical rays are directly over the Tropic of Cancer. The winter solstice, December 21st, which is where the sun's vertical rays are directly over the Tropic of Capricorn. Autumnal equinox, September 22nd, the sun's vertical rays are directly over the equator. And the spring equinox, where the rays are also directly over the equator. And this is just another picture illustrating these changes. This shows you the length of daylight versus latitude. So we were at about, what was it, 42 degrees. Okay, so we're right in here. So at summer solstice, we're getting almost 15 hours of sun up in Jamestown. And at winter solstice, we're just barely getting 9 hours of daylight during the winter season. But we need to understand how this solar radiation is approaching the Earth's surface to really start to understand weather changes in our atmosphere. So we're going to talk about the relationship between energy, heat, and temperature in the atmosphere. So first, we need to understand what energy is. So we're finally busting out that great equation, E equals mc squared. We're actually going to use this. So energy is actually the mass times the speed of light squared. To understand mass then is the energy divided by the speed of light squared. The universe is made up of energy and matter. Okay, energy and items that have mass. That is the entire universe. Matter is anything which has mass and occupies volume. When we talk about energy, this is the capacity to do work. Specifically, when we talk about the atmosphere and weather, we're talking about heat energy. Okay, the motion of atoms or molecules in substance. The higher the heat energy it has, the faster its atoms move. Temperature is our way of measuring the intensity of heat energy. Higher temperature, higher movement. Lower temperature, less movement. Heat is always transferred from warm to cold. Okay, objects with more heat energy to objects with less heat energy. It's transferring all that movement of atoms, and it's creating movement in those less or in those more stationary atoms of the cold item. So coldness is really just a description of matter with less heat energy. There are three mechanisms of heat transfer: conduction, convection, and radiation. Conduction is heat transferred through matter by molecular activity within a substance. Convection is heat transferred through matter by mass movement or circulation. Radiation requires no substance for travel, and it moves as electromagnetic radiation in all directions at the speed of light. Okay, so conduction is like if you touched a handle of a hot pot, and the heat in that pot, heats up the handle, and as you grab it, that heat energy is transferred directly from that handle into your hand. Convection is when you're boiling a material and the molecules at the base closest to the heat source heat faster. They start to increase in energy. They actually rise up, disperse their energy. As they disperse it out, they lose it. They cool down. They start to sink back down, so you get this rising and sinking motion. And finally, radiation is just all that extra heat you would feel from your heat source, such as a fire or your stove, that's not being absorbed directly by the material you're cooking. Sorry guys, it's been a really long day. Electromagnetic radiation is the transfer of radiant energy by the transmission of charged atomic particles through space. The electromagnetic spectrum ranges from gamma rays, which are very short wavelengths, to long-wave radio waves. The visible part of the spectrum is what our eyes have actually evolved sensitivity to. And we cannot see infrared radiation, but we have evolved to feel it as heat. So visible light and infrared are really the two that we are able to sense. Okay, electromagnetic radiation is governed by basic laws. All objects emit radiant energy. Hopefully that helps. Hotter objects radiate more energy per unit than cooler objects because they have more heat energy. The hotter the radiating body, the shorter the wavelength of the radiation because the movement is so fast. It doesn't have that very long delayed wavelength. And objects that are good absorbers of radiation are good emitters as well. Here's a video on the EM spectrum. I will post this link for you also. Okay. The atmosphere is largely transparent to incoming solar radiation, but the paths taken can vary. So solar radiation can be absorbed. This is where radiant energy is absorbed and is converted into heat. Okay, so 20% of radiation absorbed by the atmosphere and clouds. It can be transmitted, or it can be redirected. Reflected, 20% is reflected from clouds, or scattered. Okay, you've got the scattering going on here, and you can get some scattering from the actual atmosphere. You can get reflected or scattered by the Earth's surface. And 50% of the solar radiation is diffused radiation absorbed by land or sea. Albedo is the term we give to the amount of total radiation reflected from Earth's surface. Earth's albedo is about 30%. Okay. So we talk about absorption of solar radiation. This is where gas molecules absorb the energy and transform it into molecular motion, which is detected as a rise in heat. So it absorbs the energy, increases the heat. And the atmosphere only absorbs about 20% of incoming short wavelengths. Nitrogen gas doesn't absorb solar radiation efficiently. Oxygen gas and ozone absorb UV radiation efficiently, which accounts for the higher temperatures measured in the stratosphere. So remember we talked about those temperature changes? So this is why the stratosphere has a higher concentration of oxygen O3. It's very efficient in absorbing radiation, so it increases in temperature. And water vapor in the atmosphere is an effective absorber of solar radiation. Therefore, the atmosphere doesn't actually get the bulk of energy from the sun. It gets the bulk of its energy from being heated by the Earth's surface. Okay, and you hear people talk about the greenhouse effect. So to understand the greenhouse effect, Earth absorbs about 50% of incoming solar radiation. So the Earth's actual surface absorbs 50% of all solar radiation. Sorry guys. Whew. It then re-radiates its energy back in the form of longer wavelength infrared. Okay, so it's coming in a short wavelength UV and is re-radiated as long wavelength IR. The atmosphere is able to absorb the IR effectively, and therefore the atmosphere is heated from the ground up. So remember I said the atmosphere warms up because it absorbs the heat radiated from Earth's surface. So the Earth is basically just re-radiating from the sun, but it's this bouncing back up that is what's being absorbed in the atmosphere. Some of it irradiates into space, but the rest is redirected within the atmosphere and back to Earth's surface. So as it reflects up, it gets bounced around, comes back down. Then the more gases in the atmosphere that can absorb that IR, like carbon dioxide and methane, the warmer the Earth's surface. Because as it's being absorbed up, it's not getting through, it's not being released into space, it's being held here and just bouncing back and forth. Okay, so this is just giving you an image of that. So human activities have likely introduced excess greenhouse gases into the atmosphere. This higher concentration means more heat is trapped within it, and more heat trapped means the Earth's average temperature must rise because not as much is being lost to space. That heat energy is being transferred back and forth. Rising temperatures can alter patterns of precipitation, evaporation, and heat transfer, causing long-term climate changes. Climates have changed repeatedly, sometimes radically, during Earth's long geologic history, but man's introduction of excess gases is a new phenomenon. Gases in the atmosphere act like the glass in a greenhouse, allowing the UV radiation to pass through, but trapping the IR and increasing heat. Okay, so this is what we're talking about. So here's a natural greenhouse effect would occur. But what happens is we get more gases, less is being escaped into space, and more is being emitted back. Scientists are able to study these changes by looking at atmospheric CO2 that has been trapped in glaciers and in ice cores and in some rock units over time. So here we're looking at a graph of average global temperatures and a graph of atmospheric CO2. And you can see that we have some drops in global temperatures. These are our significant ice ages here, where the temperatures have dropped to extremely cold, 10 degrees as an average global temperature. And these tend to relate to changes in our CO2 levels. So what does it tell you about Earth's temperature and carbon dioxide levels during geologic time? So take a look at that, really focus on this, see what you can glean from this graph. There we go. So here's a close-up of the tail end of the graph, so this part right here. So we're looking at the last 650,000 years. So we've got our drops and our peaks, and it's been pretty repetitive, following a similar path, similar height for our peaks. And then we hit 1950, and all of a sudden we've got this straight shot up, really from probably late 1800s, straight up to 2012. The rise, while low in respect to Earth's history, has occurred in the last 200 years, which corresponds to the beginning of the Industrial Revolution. Computer models and some empirical data suggest that levels of CO2 above 400 parts per million, I am really sorry guys, I don't know why I'm so tired tonight, may be a tipping point for long-term climate change. And if I remember correctly, we have hit that 400 parts per million in terms of CO2 levels in the atmosphere. Okay, so this is just looking at some more charts of human impact on CO2 levels in Earth's history and temperature difference comparing 1951 to 1980. So you can see all the dark reds and oranges. Okay, we've had a global temperature increase in the last 50 years. So what is our impact on global climate? Okay, higher maximum temperatures, more hot days and heat waves over nearly all land areas is essentially guaranteed. We're looking at a probability of greater than 99%. Higher minimum temperatures, fewer cold days, frosts, and fewer cold waves over nearly all the land. It's very likely that we have frequency of heavy precipitation events occurring or increasing over most areas. And it's also likely that we'll have drought area increases and changes in intensity of tropical cyclones. So why does temperature vary? Why do we have these variations occurring? First, it's based on how much solar radiation is received, most importantly dictated by our latitude, right? The different heating of land and water. Land heats and cools faster than water. Water absorbs heat to a greater depth than land and then mixes temperatures better than land is capable of doing because you have the interaction between the water molecules. Our surface doesn't have that mixing that occurs. Altitude can impact that. Geographic position, cloud cover, and albedo. Snow has high albedo, so it reflects a lot of the radiation. Soil has low albedo. It absorbs more of the energy. We also have the temperature variations of latitude. So at the northern and southern hemispheres, we have basically zero variation within the temperature. Once you hit 45 degrees latitude in the northern hemisphere, we have about a 23 degrees Celsius variation over the course of the year. But in the southern hemisphere, we only have about a 6-degree variation. Okay, and we discussed that last chapters when we talked about the ocean. There's very little land mass in the south, and so it doesn't have as abrupt seasons because of the movement of the oceans there and the limit of the actual land mass that occurs. And here's just looking at temperature variations within geographic locations. So here we've got the same latitude, but we have Vancouver, which is a marine region, versus Winnipeg, which is deep within the continent. And the ocean actually has an impact on these. Okay, you see Vancouver tends to stay warmer and have less of a difference between its warm and cool regions, whereas Winnipeg continental has those very cold lows and slightly warmer highs. And this is because Vancouver, being right on the ocean, has that warming effect because the ocean is a good receiver and emitter of that heat energy, right? So it stabilizes the temperatures a little bit and carries that over to the landmass right near it, so it helps stabilize that region's temperature so it doesn't have these abrupt changes. La Paz, Bolivia has a high altitude in the Andes and compared to Concepcion. Both of the same latitude, but the altitude keeps its monthly temperatures lower. Here we go, looking at the difference between cloud cover. So this is from Peoria, Illinois. So on a clear day, you have the very cool temperatures in the morning, and as it stays clear, you have a bunch of radiation coming in, it warms it up. But those clear skies in the evening allow more of that heat to be radiated out from the Earth into the atmosphere and potentially into space. On an overcast day, it is radiating more of that Earth's heat back because of cloud cover, allowing less of it to escape, or allowing less of the sun's radiation into the atmosphere to our surface, so it's not letting it warm up as much, so it keeps those changes less abrupt. Here we're looking at an isotherm map. This is a contour map showing lines of equal temperatures for a given time period. So this is for January. This is giving the average sea level temperatures for January. Okay, so these are our isotherms. You can see they tend to relate to our latitude and longitude a bit. Here's one for July. Okay, you see it looks a bit different than our January one, right? We're missing some colors up here. This portion looks a little larger. So how are the isotherm patterns different between the two maps? And then why are they different between the two maps? And why do they trend east to west and not north to south? And which portion has the greatest difference in mean temperatures? So the isotherms are different between the two maps because if you look, July, we have our warmer isotherms shifting kind of toward the northern hemisphere. Here's the equator, so they're shifting north of the equator. And in January, they're shifted south of the equator because we're looking at the change in Earth's orientation to the sun, right? In which latitudes are getting that direct solar radiation. So that's why they're different. And they're east to west, not north to south, because it's based on the latitude. And then again, the axis tilt towards the sun. And which portion has the greatest difference in mean temperature between January and July? Just take a look and see. I don't remember exactly that. It's in the northern hemisphere. I think it's like this isotherm. But it's because the landmass, like we said, are bad absorbers and emitters, right? So it is more greatly impacted by radiation changes. Whereas the southern hemisphere is mostly ocean, and that absorbs the energy, redistributes it to its depth, and does a lot of mixing, so it's able to really smooth out its temperature curve. So it maintains a bit more of a stability than the northern hemisphere. So, quick summary. Temperature decreases from the tropics to the poles, so as we move from the equator north or south. Isotherms shift latitude north or south with season, and isotherms are modified by the ocean currents. Okay, those ocean currents are, like we talked about in our last chapters, are mixing and are distributing that heat energy. Isotherms variations are greater over land than water because land is a poor